Hello everybody, I know I said the last video, that was the last video on thermal radiation laws, but the video is getting pretty long, and I want to go ahead and separate out the Stefan-Boltzmann law examples that I'm going to work into its own video, so hopefully you can ground yourself in realizing that the way that we're going to work with the Stefan-Boltzmann law in this class really isn't that bad. So let's go ahead and get to it. I'm going to do a little bit of equation work to start with, but then we're going to go directly into how you can work with, we'll see the power of how Stefan-Boltzmann's law works, and then we're going to go into running it through examples of what you should expect on, say, quiz number 3 and exam number 2 and in the homeworks. Although in the homeworks I push it a little bit further than what we're going to go over in this video. Okay, so I just want to show you how we can think proportionally with using Stefan-Boltzmann's law. And most of the time, I'm not going to have you worry about things like the radiative flux values. I want to just keep things in terms of energy. It's a little bit more direct. It's a little bit something that's easier to understand. So I will always have, or at least for quizzes and homeworks, I'm going to keep the sizes of the objects the same. So you don't have to worry about that per square meter part. So let's consider two stars, star A and star B. They each have their own surface temperatures. The temperature of star A has temperature A. This temperature of star B has temperature B. And you want to go ahead and you want to figure out the ratio of how much energy they're emitting per square meter per second compared to one another. If they're the same size, then this is going to be the total amount of energy that they're emitting compared to one another. So I'm giving you the temperature, I'm asking about the energy. Your brain should be screaming Stefan-Boltzmann's law. And notice that thinking proportionally, we're always comparing one thing to another thing. So we're going to have comparing one star to another star, star A to star B. And I want to go ahead and show you this so you can see how the thinking proportionally really comes out and how it works and why we just consider by how many times something changed. And that will hopefully be very helpful for you to do Stefan-Boltzmann's law, because then if you can remember temperature to the 4th power, you're going to be set. So let's talk about the ratio of the flux of star A to star B. So we have the flux of star A, Stefan-Boltzmann's law of star A, just equals, I'd take sigma, whatever the temperature is, and raise it to the 4th power. And I could go calculate, 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 and I'd get some answer in watts per square meter. I could do the same thing with B. It would be the Stefan-Boltzmann constant times the temperature of B raised to the 4th power, and I could calculate, 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 calculate. And I get an answer in watts per square meter. But maybe I just want to know the ratio of the flux of A to the flux of B. So if I want to do the flux of A compared to the flux of B, I'm going to walk you through each one of this. So the flux of A equals sigma times the temperature of A to the 4th power, just this part right here. The flux of B equals sigma times temperature to the 4th power, or times the temperature of B raised to the 4th power, just this part right here. So it's just that divided by that. And notice that, sigmas go away. They cancel it out. Sigma divided by sigma is 1. So now I just have the temperature of A to the 4th power divided by the temperature of B to the 4th power, which I can pull that 4th power out, and it's just the ratio of the temperatures. The temperature of A divided by the temperature of B raised to the 4th power. And this is just telling you temperature of A divided by temperature of B. That's the ratio, just how many times A is compared to B, the multiplicative factor, the thing that we've been tracing so much, been paying attention to so much to think proportionally. So all you have to do is take the ratio of their temperatures and raise that to the 4th power, and you've calculated the ratio of their fluxes. If they're the same size, so that means ignore anything about the area, then you have done the ratio of the energy that they're emitting. Let's go ahead and walk through this just like I did with Wien's law. Let's walk through the same examples. And here I'm going to assume that all the objects are the same size. Well, and the Wien's law, the first example I did was a star with a temperature of 10,000 Kelvin, a pretty hot star. I could calculate that out. I could use the full version of the Stefan-Boltzmann's law to figure out that its radiative flux equals sigma, this number right here, times 10,000 is temperature raised to the fourth power. You can crunch that into a calculator if you want to follow along, but you would end up calculating out 5.67 times 10 to the 8th watts per square meter. These are the kind of things I'm not going to have you calculate, but I'm just doing this because this is the star that I'm going to compare the other stars to. So I want to know what this value is, so then I can show you how much simpler these problems can be if you just think proportionally, if we're going to compare to some standard that we know. Okay, so the second example that I did is a star that has a temperature of 30,000 Kelvin, about as hot as stars can get. The surface temperature of 30,000 Kelvin. So I can calculate the flux. It would equal sigma, that number, times 30,000 raised to the fourth power. Punch in those numbers into your calculator, and you'll get 4.59 times 10 to the 10th watts per square meter. That's a bigger number. Does that mean a whole lot to you? Probably not. Doesn't mean a whole lot to me either. I just know that that is going to be the radiative flux. It's a number. Okay, let's do the same for the 5,000. A star has 5,000. This is a little bit cooler than our sun. And I could go ahead and calculate the radiative flux using the full version of Stefan-Boltzmann. It would be sigma times 5,000 raised to the fourth power. And I'll get 3.54 times 10 to the 7th watts per square meter. A radiative flux. Energy per second per square meter. Do the same thing for something that has a temperature of 1,000 Kelvin. Calculate it out using the full version of Stefan-Boltzmann, sigma times 1,000 Kelvin to the fourth power, 5.67 times 10 to the fourth watts per square meter. That's a lot less energy than, say, these ones up here. Okay, so yeah, you could go ahead and I could have you go ahead and crunch through all the equations. And what have you done? You've learned how to plug in numbers. And then you've crossed your fingers and you hope that you put in all the numbers right and you're putting your fourth powers in all the right place. And you're not making any mistakes to get a number like 5.67 times 10 to the fourth watts per square meter. And you're like, I don't really know what that means, but I sure could plug those numbers in. What I want you to understand is that the amount of energy that something is giving off is related to the temperature to the fourth power. I want you to play around with the actual physical phenomenon that's going on. What are the connections between the energy and the temperature? So let's do like I did with Wien's law, and let's compare everything to this star that has a temperature of 10,000 Kelvin. All right, so here we have our 30,000 Kelvin star. 30,000 Kelvin is 3 times 10,000 Kelvin. It's 3 times hotter. So thinking proportionally, how much more radiative flux, how much more energy should it be giving off per square meter? It should just be, oh, it's 3 times hotter. So it should be 3 to the fourth times. Notice that's just the, I'm gonna have to bounce back a good bit here. The ratio of the temperature is raised to the fourth power. The 30,000 divided by the 10,000, that's 3 raised to the fourth power. And I could go ahead and do that. 3 times 3 is 9. And then times 3 is 27. Times 3 is 81. Or 9 times 9 is 81. So 3 to the fourth equals 81. So now I know that the 30,000 Kelvin star is giving off 81 times the amount of energy per square meter compared to the 10,000 one. Let me check my work. If I'm right and this thinking proportionally is really that easy, then 81 times this number should give me the answer for the 30,000 Kelvin star. So 81 times 5.67 times 10 to the 8th equals 4.59 times 10 to the 10th watts per square meter. Oh, hey, same answer, same answer. Okay, so that was a little bit easier than needing to know what this value is and plugging in all those numbers and making sure you get everything right and you write everything correctly in scientific notation. It'd be much easier for me to ask you how much more energy per square meter is this 30,000 Kelvin star giving off to this 10,000 Kelvin star. We know that the 30,000 one is 3 times hotter. 3 to the fourth is 81. It's giving off 81 times more energy. And now you've played with the concept of radiative flux. And you've played with the idea that that is related to the temperature raised to the fourth power. The total amount of energy something is giving off is proportional to the temperature raised to the fourth power. You are actually playing with the nature, or with how nature works. Okay, let's do another example. Let's do this 5,000. Sorry, that arrow is pointing in the wrong place. I should have dragged it down. So for this 5,000 one, 5,000 is half as hot as 10,000. It's 1/2 times 10,000. It's 1/2 as hot, 2 times colder. So the radiative flux should be 1 divided by 2, the ratio of the temperatures, raised to the 4th power. And so 1 to the 4th is 1, 2 to the 4th is 16. That's 1/16, the number. That's the same thing as saying 16 times less than the 10,000 Kelvin case. So I could take the answer of the 10,000 case, divide it by 16, and I should get this number, the 5,000 case. So 1/16 times 5.67 times 10 to the 8th gives me 3.54 times 10 to the 7th. Do these answers match? Is this the same? Hey, yep, they match. A little bit easier. 2 times colder. 2 to the 4th is 16. It'll be 1/16 the amount of energy. 16 times less energy per square meter. And let's do this last one. So 1,000 Kelvin is 1/10 of 10,000 Kelvin. It's 10 times colder. It's 1/10 as hot. So the radiative flux should be that ratio of temperature, 1/10 raised to the 4th power. That's 1 over 10 to the 4th, 1 over 10,000. 1/10,000th the amount of energy per square meter. So it should be 10,000 times less than, saying the same thing. The 10,000 Kelvin case. So let's just take 1/10,000, 1 over 10 to the 4th, times this number, 5.67 times 10 to the 8th. And that gives me 5.67 times 10 to the 4th. This should be the same number as I have here. Oh, same numbers, they match again. So hopefully this shows you how we're doing this thing proportionally, where all these numbers come from, why we're just concerned about, say, the ratio of the temperatures, how many times different is one temperature compared to the other, what is the ratio of their temperatures, and how that all works out. But I do want to give you some kind of easy, simple, classic examples to work with, and this is the kind of thing I expect you to reproduce on quizzes and exams. So let's do some more examples. If you need to take a break, come back with a sheet of paper so you can take some notes. And let's run through 3 more examples. And these are the kind of examples that you should expect to be able to work on a quiz or an exam. Okay, so in this one, I'm gonna have everything be the same size. And we're just gonna consider some patch, some square A compared to some square B, or some left. So one on the left compared to the one on the right. I'll give them temperatures. So A here is going to have a temperature of 300 Kelvin. B is going to have a temperature of 600 Kelvin. Or what I'll probably do is just tell you that B is 2 times hotter than A. So object B is 2 times hotter than object A. By Stefan-Boltzmann and thinking proportionally, I know if I want to figure out how much more energy B is giving off compared to A. It's hotter, so it's giving off more energy. Then all I need to do is take that, it's 2 times hotter, raise it to the 4th power, and I should get my answer. I have them as the same area, so it will be a direct comparison of how much energy they're giving off. So since energy is proportional to the temperature of the 4th power, this 2 times hotter, 2 to the 4th is 2 times 2 times 2 times 2 is 16. This one is emitting 16 times as much energy as this one is. Not that bad. All it was is figure out what the temperature difference is. This one's 2 times hotter, so it's emitting 2 squared, 16 times more energy. That's really all I'm asking for a lot of these, for quiz questions and things like that. Although I might do it the other way, where I'm always going to be comparing the one on the right to the one on the left here, where now I have square D here is cooler than square C. So D is 1,000 Kelvin, C is 5,000 Kelvin, D is 5 times colder, 1/5 as hot. So how much energy is D giving off compared to C? So I take the ratio, it's 1/5 as much energy, and I raise it to the 4th power. 1 to the 4th is 1. 5 to the 4th is 5 times 5 times 5 times 5. Multiply that out, you get 625. So it's 1/625th as much energy. So object D is releasing 1/625th as much energy as object C, which is the same thing as saying that object D is releasing 625 times less energy. And hopefully you're getting used to how you can use language to describe things in multiple ways. So 625 times less is the same as saying 1/625th as. And let's do one final example just to show you how insane things can get. So here we have a 20,000 Kelvin temperature object, and here we have a 200 Kelvin temperature object, a very, very hot star to a very, very, very cold nebula, or a planet, something like that. So object F here is 100 times hotter. So 20,000 divided by 200 equals 100. It's 100 times hotter. How much more energy is this square F giving off compared to square E? Well, take the ratio of their temperatures. This one's 100 times hotter. So it should be giving 100 to the fourth. That's 100 is 10 squared. Raise that to the fourth power. Remember my exponent rule. Okay, 10 to the eighth. 100 million times more energy. It's just 100 times hotter, but it's giving off 100 million times more energy. Okay, so that's a lot of examples, and I can hear they're doing some construction. Hopefully you can't hear that over the mic, but I'm gonna go ahead and end the video here, and hopefully you know how to work with Stefan-Boltzmann's law now. All right, thank you for tuning in.